He is an associate professor in the School of Electrical Engineering and Computer Science at Washington State University. He received his PhD degree in electrical engineering from Texas A&M University in 2011. His research interests include operational security of inverter-dominated power systems, focusing on stability, protection, and control challenges of grid integration of inverter-based resources. Dr. Lotfifard is a senior member of IEEE and serves as an editor for the IEEE Transactions on Sustainable Energy. Welcome, Dr. Lotfifard, to our ESIC seminar, and we look forward to hearing from you today on fault-resilient massive grid integration of inverter-based resources.
Thank you, Anamika, for the introduction. Let me share the slides so see that now. Oops. So can you see the slide and the presentation mode?
So we see the slide, but it's not in the presentation mode. We're still seeing your slide sequence on the side.
Oh, okay, so let's see that. Maybe. But now?
No, it's still the same view we are seeing.
Oh.
Maybe it's what you're sharing is that particular view.
Yeah, let me maybe close it.
Yeah.
Okay, so then let me just open it again. Open, share. How about now? Is it? No?
It's still the same slide. So if you click that button on the bottom, the one that goes to screen share mode, does it change anything? The presentation mode, there's a button at the bottom.
This one? You're saying that at the slideshow? Yeah, I press that one. Yeah.
Okay. It's probably sharing a different. It's sharing actually presenter views, but we can see your slide. I think we are fine. It's just it's a little bit smaller.
Yeah, if you have two monitors, then it will be on the other monitor, and on the top left corner, you can swap the presentation window on the other monitor.
Other one? Yeah, I have two monitors, so.
It's probably showing the other monitor. Yeah.
Oh, so then what should I do for that one?
On the top left corner, second tab, you will see swap window. Then you will be able to swap the window.
So here on the power
on the other monitor.
Okay. Display setting, you mean? Okay.
Let me see if I can find. Yes, display setting. That's right.
How about now? Is it working or?
Display setting, and then you can do like
yeah, I switched that. So
yeah.
I display setting, and there is 1 and 2.
Swap settings. Swap presenter. Sorry, window.
Where is that one? So.
Oh.
Rearrange your display. So let's see that. Maybe identify. Yeah. Yeah, it's identify which one is one.
Said, maybe we can go with your original presentation. Yeah. I think that's going okay.
Okay, yeah, I will go. Yeah, let me see that if I can.
Yeah, it's showing a big black window. If you can close that, I think that should be fine. Yeah, I think this is good.
Let me just make it smaller.
Yeah,
this
exactly.
Yep, and this side. Yeah, maybe.
This looks good. Yes.
Okay, let's go like this. Okay, yeah. Okay, thank you. Sorry for this.
No
difficulties at the beginning. So yeah, first of all, thank you for having me for this seminar. So hopefully you find it useful. So the topic of this seminar, I'm talking about that is fault resilience, fault resilient massive grid integration of inverter-based resources. So the outline is that at the beginning of the presentation, I will talk about the what are the issues that we are working on and why they are important to be addressed. Then I briefly review some of our proposed solution for the problems that we will discuss in next few slides. Then specifically, I will spend more time on one of the projects that we had on the co-simulation platform for capturing dynamic interaction between vulnerable protection function and power grids. So that is mainly useful for kind of dynamic security assessments when you want to try to integrate renewable to the grid. Then some of the mitigation solution will be discussed, and then I will summarize my talk. So the challenge is that as we integrate more inverter-based resources to the power grid, which could be in the form of wind power, solar power, energy storages, HVDC system, we will face the new dynamics and new fault response characteristics of these devices. And we have observed this differences in recent major power outages. I have listed some of them here, but there are so many more cases that has happened in the last few years. For example, example A that I have listed here is related to the 2019 UK's blackout that was mainly due to large integration of the DGs at the medium voltage distribution system and misoperation of the protection due to fault at the transmission line. Then we have very famous blackouts at the 2016 in Southern Australia blackout. Then the Southern California event also is very well-known events that actually that one the sequence of the event at in short period of the time, basically in few months. So, and one of the event that over there happened was the sub-cycle over voltages. That was kind of new for the inverters at that time. So there are so many research activities on that type of over voltages. Then we have 7 hertz power and voltage oscillation at First Solar Power utility scale PV power plant. That basically it happened when the fault happened in the system and some of the line goes out, then the system become weaker. So the controller were not designed for such a weak power grid. So then they had the oscillation and the outage of the PV farm utility scale PV power plants. Then also we had the very famous outages of wind turbines in German power grid. So the problem here was that when the fault happened in transmission line, due to the post-fault, again, that was the post-fault temporary over voltages that caused the wind turbines are disconnected from the grid. And also we have another case that it was in the northwest side of the China. So they had the same problem of the post-fault temporary over voltages. So these are kind of the events that happened that they were mainly due to different dynamics. We do have such problems in traditional power grid as well. So that's not the nature of the event is not new, but the way the system has responded to such events were kind of unexpected. So which initiated so many research and also T&D activities. So therefore, what I see here in my group, we have observed these events, and what we have determined is that we need grid integration impact assessment and fault resilience enhancements tool to enable the more informed and reliable massive grid integration of IBRs. Specifically, we should propose methodology for modeling, analyzing, and enhancing fault response behavior of IBR-dominated power grids. So why that's important? Because it directly affects the operational security of power grids. And because by definition, based on NERC, the operational security means the ability of power grids to tolerate large disturbances, such as faults and outage of the large units. So therefore, any solution that can help for enhancing the response of the system to the fault can directly affect the operational security of power grid. Some of the solutions that we have worked in last several years, it has been toward both transmission and distribution system. I picked up some of them that I can discuss today, and of course, if you are more interested in details, please do let me know. I will be happy to discuss in more details. So, so one of the, for distribution system, two of the enabling technology that we could think of were creating microgrids and also fast restoration of power systems. So of course, there are so many more technology over there, but these are where we work on that one. So as far as the microgrid goes, when the fault happens, so one way to enhance the fault response of the system is that we create the microgrids. So for microgrid, when you have an intentional islanding, so you have more time, you can coordinate everything, and then do the transition between modes of operation of the microgrids. But when the fault happens, you have unintentional transition between modes of the operation of the microgrid. So therefore, it's not pre-planned for that the specific scenarios. So therefore, we have to develop the methods to make the seamless transition between modes of operation, especially if you have grid forming and grid following inverters that you are switching between modes. It depends on the status of the microgrid. So then the issue that happened over there, you have sudden change in the strength of the system. So therefore, what happened? You have a small islanded network with a significant reduction in the strength of the system in short period of time. And also you have a switching between modes of the inverters. So therefore, over there, you see that, and if you can easily observe in some of our simulation cases and reported real world cases, that you have some unintentional oscillation in the system that it may causes that you are not be able to successfully transition to the post-fault condition. So therefore, what we propose over here, we said that, okay, we don't want to change the controller of the inverters because there are so many advantages over each controllers that manufacturer picked up. So that's not the random selection of those. So we want to keep the strengths of those algorithms over there and we use them. But at the same time, we want to overcome such problems that we have seen. So therefore, we have proposed supplementary controllers. So which means that we don't change the tracking problem of the controller. We just improve the transition of the controller. And when it goes to the quasi steady state, basically output of our controller would be 0. We don't change anything. So simulation result, it has shown that it could significantly help these transitions. Another consideration as far as the microgrid goes. So when you have a microgrid successfully transition to the post-fault condition, then the question is that can you sustain the microgrid for longer period of time or not? So one issue is that there are two main issues. So one is that can you coordinate the frequency response of the system, and two is voltage consideration. So we vote for voltage because voltage were more challenging as far as the coordination of the microgrid concern. So, but frequency is the same procedure. We can apply the same algorithm over there. So the idea was that we want to make sure that the inverters can exchange limited information with neighboring inverters and provide exactly the same solution if you had the centralized controllers. So this has a lot of application and advantages because you can have a less expensive communication system. You can have fault-tolerant communication system. You can have fault-tolerant control system. There are so many advantages of going from single centralized controller to fully distributed controller. So that this one, we work with our control system colleagues and we work on their protocols that they have developed for different applications, but we mainly utilize that for the power system application. And here we developed the new model of the inverters such that it can be compatible for such a controller. So that was basically main contribution that we had here. So that how to control this inverter independent on the system. So therefore, they just need a exchange few information with neighboring controller, and we prove that they get the same result as if you have a centralized controller. The same concept we have applied to the multi-terminal HVDC system as well. So this is mainly for transmission line. But the concept, of course, the controllers are different, the models are different, but the concept is basically very similar. So basically, you want to have if you have HVDC system that works in the basically multi-terminal HVDC system, and you have distributed group control. So you want to have a secondary controller, because we all know that the group control cannot especially for voltage control. For frequency they can, but for voltage control they cannot provide a fair power sharing in the system. And also you have a steady state error, because that's the nature of because group control is nothing except the proportional controller, and we know that proportional controller you have a steady state error. So therefore, how to get rid of that steady state error, and also make sure that the converters, they have a fair power sharing among each other. You have to have a secondary controller. Traditionally, it's done using centralized controller, but even here is probably even more important, because, for example, if you look at the case of Europe, each converter can be in different country. So if you have this fully distributed controller, you don't need to have one centralized controller to own all the data. So they just need to have a limited information exchange between the converter stations. So that's another advantage of going fully distributed. Another aspects of the fault resilience is you want to make sure that you make the power system restoration as fast as possible. So one main component here is the fault location identification. So this topic, I'm working on this one in last maybe 10 plus years. So, but recently we are very fortunate to work with the PI at Georgia Tech, and that's a funded project by the DOE, and we are working with 3 main utilities at different part of the US. So at Avista, at basically Northwest, we have a Dominion Energy at the Northeast, and we have a Southern Company at basically in Atlanta. So these are basically different geographical places, and we will implement all of this algorithm. The whole project has so many different components, but the component that is related to our group is related to how to identify exact location of the fault, and we will prove everything using experimental data. So the main concern that we are looking for here is that if in distribution system, which is very common, so we have more limited number of measurements installed along the feeder. So the question is that how can we use this data, especially if we have a multi-source data and heterogeneous type of data. By that, what I mean that we have analog data or oscillatory data, which is basically means the voltage and current measurement. We have a status data, which could be fault indicators. It can be logs of the protection devices, and so on and so forth. So basically, you have continuous and you have discrete data. And also you have synchronized data and unsynchronized data. You may have a legacy system measuring devices that just provide the amplitude. Or recently, people talk about the installing micro PMU at distribution system. So then the question is that you don't have a kind of homogeneous data. You have different type of data. The question is that how do you want to use this data? So therefore, we need a fault diagnosis model for faulted inverter-dominated distribution system, because not only the data have different natures. Also, the response of the system is different, which I will discuss in few next slides. So therefore, what we are trying to do, we are developing hybrid models so that it uses the discrete event system modeling and continuous system modeling. And we are combining these two models to enhance the fault location identification result. So one of the issues where, of course, we have to address in distribution system, we have partially observable system. So this is the work that I'm working with two of our computer science colleagues on how to use the data-driven model and physics-based model to solve the problem of the partially observable distribution system, which has so many applications, but one of the application is the fault location identification approach. Another problem here is that traditional generator, which basically synchronous generators, we model that as a voltage source model behind the series impedance. But in inverters, you model that as a based on the modes of operation. You basically model as the current voltage dependent current source. So therefore, this totally changes how you do the short circuit analysis. How do you do fault analysis? So therefore, that's another challenging problem, challenging part of the problem. So therefore, how to combine all of these models is very interesting topics that we are working on. That we have made some progress, and we are working. This is a continuing projects that we are working on. But the goal is that we want to identify the fault as soon as possible. So once we identify that, then all of the system restoration programs and so on and so forth can be executed. So these were two applications for distribution system. So for transmission line, I have picked up three, but I will go faster because we don't have that much time. So one issue for transmission line is that can we make sure that the IBR, so here is PV system, the next slide is fuel cells, but in general, inverter-based resources, can they tolerate the large disturbance in the grid? So basically the concept of the fault right-through capability. But the problem that it shows here, there are so many problems here because it mainly goes on the grid synchronization stability problem. So you have to go to nonlinear study because when you have large disturbance, so any models that works on the linearization model basically doesn't provide realistic result. So therefore, we have to go through the nonlinear problems. Recently, we worked on the new controller that basically has been proposed for the controlling the arms of robots. So we utilize those controller and we modified that to be applicable for applications. So and we applied for the PV systems and fuel cells. So, but the main contribution over here is that when you have a nonlinear, when you have large disturbances, one of the main difference is that saturation of the controllers come to play. So therefore, how to take care of that? Traditionally, what we do in power grid, usually we use the anti-wind-up. So, but the anti-wind-up, you can make it as complicated as possible and complex model, but usually we don't use it for power system because then the implementation is a challenge. But those that are commonly used are basically the tuning of those are mainly based on heuristic approaches. So and there are so many reports that in certain conditions they don't operate as expected and so on and so forth. So therefore, the main objective we had here was that can we come up with the controllers that have a rigorous proof of stability and we know what's going on there, at the same time be simple and easy to implement. So that's why we picked up this controller, and still it's ongoing task in our group. We are working on to see that how we can get more out of that one. Another aspects of the grid synchronization and stability that I mentioned that was the problem in the first solar PV power plant in Arizona that happened that when sometimes you have a system which is weak. That's another one problem. But sometimes you have a transition to the weak system. So this is kind of more complex cases. So therefore, what we have done that we have done supplementary controller here as well to take care of the problem that we have with the PLL. Again, in grid forming converter, you don't have PLL, but still you have a transition in the strengths of the system. So therefore, this methodology can be used for both grid following and grid forming controllers. So that's the, and also again, this is ongoing projects. We are trying to address. There are so many problems here, so that is a little bit more complex than we expected. That so we are working on this one. So another aspect that, and which is very important aspect, is that developing dynamic security assessment tool for inverter-dominated power grid. So that whole goes to modeling. So far, what I discussed were basically controller for implementation in real-time application. But another problems that we should address that is developing softwares and programs that we can use that. One of the very important simulation platform that we have to go through is that how to capture realistic fault response model of the inverter dominated power grids. It has so many aspects. It has the how to implement the aggregated dynamic model of the PV farms, solar farms. How do you capture the dynamic interaction between protection and power grids? So, and also how to integrate different controllers modes in the system. So therefore, this is again the projects that we are working for the last several years, and also recently, actually that is started last summer. So we have a PSEC projects that we are working on these aspects of the problem. So how to develop the dynamic security assessment that basically we're using co-modeling and co-simulation of different aspects. The response of the how to realistically model the dynamic response of the PV and solar farm, how to capture interaction between protection and power grid, and of course the different aspects of the power grids. This one I will discuss a little bit in more detail in a few minutes. So another aspects of the fault resilience in transmission line, again, it goes back to the root cause analysis. So that is the problems that we have faced in renewable energy as well. So why that's important for renewable energy? Because again, you have different fault characteristics. So therefore, how do you develop the root cause analysis? That's a challenging problem that we are working on that one. It goes back to how the protective relay respond to these different fault characteristics. So there are so many relay functions that they misoperate. Some of them, they are well known and they are well documented and people were aware of that. Some of them we are trying to even go further detail in the measurement change of the protection system and then integrate in this root cause analysis program that we have. One of the byproduct that project was also that because once we have that root cause analysis, it can be applied for cyber attack too. So basically we work with our colleague, Dr. Adam Han, on how to develop that root cause analysis model that we originally implemented for physical fault, but it can be applied for cyber fault as well. Another aspect, I think that is the last slide that I have on this aspects of the fault analysis. Another aspects of the renewable energy is that we are working with the problem here is that we are working with the hybrid system. We have switches in the system, we have a mechanical part, we have electrical part, and the switching aspects on that one. Then to have a fault resilience, we will have to detect the fault as early as possible. So that's basically in literature is called the early detection of the fault. So basically how to do that, because if you do that one, then you can prevent the unexpected outage of the line. So component. So here what we have done, we have utilized the multi-physics graphical model based on the, it looks at the how energy in the device is transferring from different points. So therefore, we are not limited in one physical domain. We are not limited to electrical. It can easily transfer to mechanical part, hydraulic part. And also the main component was that how to get rid of those switching. So because those switching is the main concern for early detection, not for protection. The protection is not, basically it's mostly done using the fast fuses. So we can do that fairly straightforward. But for early detection, that's the issue. So that's those switchings are main difficulty, which we try to address that using this new modeling that we had, and we got very interesting result. But it can be, of course, always you can extend it. So by all of this, what I wanted to convey that the fault resilience and enhancing operational security of inverter-based power grids requires new modeling, new simulation tools, and new controllers. So that's the how, from my point of view, that's how it should be attacked. We should attack the problem. And the interesting thing is that we shouldn't do that in separate approaches, because if somebody just focus on one aspect, we'll miss other aspects. In my group, we learn a lot by proposing the holistic method. So how different aspects are impacting each other and so on and so forth. So my understanding is that these aspects should be done in a holistic approach, not the isolated approach. But for the sake of time, let me just go to the one of the projects that I picked it up, and I will go fast. So basically, we have almost 30 minutes. I try to finish that in 20 minutes, and then we have 10 minutes for Q&A. So the problem that we captured here was how to develop the co-simulation platform to capture the dynamic interaction between protection function and power grids. And we have seen that in so many blacks out that happen in the power grid. So the protection function that are dependent on power system dynamics, they may misoperate. And they have been shown that in ERCOT, we have seen that in 2003 blackouts, we have seen in so many recent power outages of inverter-based devices, we have seen that. So they should be, so the bottom line is that how we can integrate those responses in dynamic security assessment tools to get a more realistic response of the system when I study the dynamic security assessment. So that was the main motivation here. So one of the very famous protection function that may misoperate is the distance protection, and mainly when you have power swings, so the apparent power that is measured by the relays may appear as the actual fault. So the conventional method to solve this problem is that we install the blinders. So, and then we say that the assumption is that power swing is slower than the trajectory of the movement of the impedance in power swing is slower than actual fault. And so therefore, based on this assumption, we put the fastest, we make the assumption on the fastest power swing that happen in that area of the power system. Based on that, we have a time delay between these two blinders. So from the time that the trajectory of the impedance enters that blinder until it goes out, if it is more than certain time delay, the fault, that's a power swing. If it is less than that one, it's fault. So basically, that's the main idea behind these blinders. But the problem here is that there are so many cases, and we have shown that. So next few slides, I will discuss that one. So you may get the faster power swings over there, especially if you have a renewable energy with low inertia. You get that one. So that is not, that is something we will face that. So therefore, the problem is that how do you want to differentiate between of course, this is three-phase fault. The single-phase fault, that's kind of easier to detect that because that's asymmetrical fault. But the symmetrical fault and power swing in low inertia power system is a challenging problem. So therefore, this is kind of one of the vulnerable protection system that should be integrated into the dynamic security assessment. Another one is that loss of excitation of the protection system. So the concept is similar to distance relay because here also we look at the trajectory of the impedance. So therefore, we have the same issue here. So there are some scenarios that you may detect the loss of LOE, loss of excitation, as actually power system swing as loss of excitation. So therefore, this is another protection function that is vulnerable to system disturbances. That's not for the fault. So therefore, it should be integrated into the dynamic security assessment. Another one is the directional relays. So there are so many mathematical proof of that. If the angle difference between two ends of the line is more than certain level, the front fault may be detected as a backward fault. So therefore, that's another function that is, and it has been observed in ERCOT system. So this is realistic type of problem. So there are some report on that one. So that that was not directly in directional relay problem. So that was more on the fault type detection. So, but that is related to this concept as well. So therefore, that's another issue that should be considered. So based on this observation, as I said, there are so many other protection functions that, especially for renewable energy, that's a ongoing project that we have. So this is actually the all PSEC projects that we had, and the report is available on the PSEC website. But we have another ongoing project on the relay misoperation detection for IBR dominated power grid. These few that I mentioned, that these are common in the conventional power system and IBR dominated. But when you have IBR dominated, we have more cases and more scenarios that the relay may misoperate. So the bottom line is that we have vulnerable protection systems. So they should be integrated in the dynamic security assessment. So we implemented this software is already commercially available. So we use that. That's a co-simulation between PSSE and CAVE. So presently, they basically PSSE purchased that Electrocon. So basically, CAVE is part of Siemens at present. But at the time we worked in this project, there were two different companies. So therefore, that was, but the bottom line, still they have that software. So that is co-simulation between dynamic study and protection function. So we have done that. We have done co-simulation platform for WEC system. So that was 20,000 plus bus system. And we have done so many contingency analysis to see which one may lead to misoperation of the protection system. So therefore, we have done so many scenarios. One of the scenarios that we showed that the weakness was some line between California and Oregon, or if I'm not mistaken, that it was going to California. So therefore, at that time, so if the swing happened over there, we observed that some protection function in Colorado misoperated, even with the blinders. Then we had this loss of excitation. Again, we observed that this one, we implemented different SEL functions, and we observed this kind of, they are not experimental data. They're all in simulation. So then what we observed that, again, the same issue. So in certain condition, if you have certain type of fault, LOE may misoperate. And we have documented this one in the PSEC report. You can read if you need more detail. So then the solutions, the different solution, I will go faster for the sake of the time. So therefore, the bottom line was that we need to have that co-simulation platform to detect how the fault propagate in the system. So that was the outcome of that study. But how to address this one? One is that solve the problem from the protection side. So we develop different algorithms. So we develop secure loss of excitation protection that can detect the power swing from the actual loss of excitation. We have done for distance relay, again, how to detect the power swing from the three-phase fault. Another way of addressing the problem to make the source of oscillation, attack the problem from that side. So that one, the way we address that, we develop the controllers such that we can make sure the synchronous generators are stable in the system. Traditionally, what it's done is basically, this is the remedial action. So one very traditional approach, this one is basically in 1970, I think 6, that was 1400 megawatt dynamic braking resistor that is installed at Chief Joseph substation. Basically, this is almost 2 hours drive from Seattle. So that's basically in the state of Washington. So this is, and if you see that, so I have the video recorded of that one. So let's see that. So once the fault happened, that braking dynamic braking resistor comes to the grid and basically absorb the extra energy. So, but this done, again, this is well documented approach. So there are some, as I say, even experimentally is implemented, but it has so many limitations. So our idea was that can we utilize energy storages for that application? So therefore we developed a controller that everything is decentralized. This is coordinating any battery energy storage that you have locally over there with the synchronous generator. So then what the main challenge here was that how do you develop the decentralized model for such a application? Because this is multi-machine problem. Some people, they work on the single machine infinite bus, but we already know that in power grid, when you have multi-machine, it doesn't address the problem well. So therefore, we have to develop the multi-machine solution. But once you go that one, the problem is that how do you kind of develop decentralized controller? So we work on that one and we developed a decentralized model for the controllers. So and once we develop this model, then the rest is how to utilize controllers. So once you have the model, you can develop so many different controllers. Over there, we use the MPC type of controller, but again, you can use any other controllers that you prefer. So over there, we developed the model predictive control approach over there, and basically the objective, that was interesting. We worked on this objective. Main objective was that, of course, you want to make sure the synchronous generator remain synchronized to the grid. And one very important problem sometimes is overlooked is that during that process, you should make sure that the voltage level at the terminal of generator is not more than certain level. Because while you are working on the transient stability, your over voltage protection devices may operate. So because you go out of the range. So therefore, these were two objectives: how to make sure this is synchronized to the grid, and also the voltage level at the terminal of generators remain at acceptable level. So then we have tested that algorithm using New England 68 bus system. Here you see that we have done so many different nonlinear controllers, and basically that green one, which is MPC plus energy storages, provide best results. So because you can have the same controller without energy storage. Still, because people have worked on that one too. So how to work on the AVR type of problem. So you just work based on the controlling AVR. But the problem is that if the severity of the fault is more than a certain level, you cannot do that one. So, and you see that here, we could improve that the result, but eventually it became unstable. So the summary of all of this discussion that I had here is that we need, as we integrate more inverter-based resources to the power grid, we need new solution for modeling, analyzing, and enhancing the fault response behavior of inverter-dominated power grid, which is needed. I mean, that is the required thing. So because we have to make sure the operational security is maintained. So there are so many challenges here, but always one thing that at least I keep in mind that very good example of this one is the basically computer companies that we have seen that in early stages, you had this on the left-hand side, you have this size of the PC. So then right now we have the even smaller than PC that at the right-hand side. So they have transitioned from over there to here. So in power grids, we are not even that bad. So we are not at the earliest stages of inverter-based integration. There are so many progress has been made, and they are all practical are implemented. But there are so many problems that shows up, and we learn as we move forward. So the whole point is that we should learn from there, and we work on that one, and that is very exciting thing to do. So, and by that, thank you. So thank you for listening to this talk, and yeah, I'm taking any question if you may have. So yeah.
Great.
Thank you, Anamika. Yeah, back to you.
Yep. Thank you, Saeed, for excellent talk. We have several questions here on the chat, but if anyone wants to ask a question, please feel free to unmute yourself and you can go ahead as well. So the first one is on basically the nature of the distributed algorithm that you said about the scale-free optimization, right, or scale-free analysis of the converter-based resources in the distribution system. So the question is that, are you considering in the distributed scenario, sorry, how is the communication going on with these agents? Are they only talking to the neighbors, or are you assuming something else?
No, that is only, yeah, that, let me see if I can. I think this, yeah, this is just the neighboring inverter. So there is nothing else. So basically here, maybe you don't see this issue because there are just 3, but imagine you have 20. So basically this inverter just need to communicate with neighboring thing. And that's the whole point of the scale free. So basically you have millions of the inverters, just the neighboring inverters should communicate with each other. So there is no communication more than that. Yeah.
And by neighboring side, you mean the electrical neighbors, right?
Yeah. I mean, yeah, exactly.
Shreshi, go ahead. I think you had a follow-up question.
Yeah, my question is actually, okay, so it is communicating with the neighboring inverters and the system is tuned according to that. Now, if the grid undergoes major changes and fully distributed algorithm, how controllers will bring the system back to the previous operation condition? Because they now don't have any reference point, right, in a fully distributed scenario.
No, you have a reference point. So the way it's referenced is point, but in centralized point, you have one centralized controller, and it should communicate with each inverter individually. But here we have this called in terms of the multi-agent controller, is called the leader node. So you have a leader over there. So at one point of your system, or it can be any point of your system. So the leaders, they will communicate, and the reason it's called the fault tolerant is that you can have as many leaders as you want. So therefore, it's not just for if centralized point, you have one person at the top and communicate individually like using a radial communication system with like the star communication. So in each individual inverters. So if that centralized controller fails, everything fails. Or the communication between that is centralized with this one. But if you can distribute that leader to several points, not just one point, you can have as many leaders that you want. So therefore, they can communicate with each other. So therefore, that's the main concern that you raised. What happens if the system goes major outages, or the communication may fail? So therefore, we studied so many things. So for example, you have a communication package drop. So if your communication even temporarily drops, what do you do? So therefore, these are the whole contribution of the distributed protocol. Yeah.
So basically, it's hierarchical. You were saying that it's distributed and hierarchical control.
It's not called hierarchical, because hierarchical means that somebody tells you to, but the distributed in a sense that you have a leader that generate the kind of what the whole thing should follow. So that one, so there is no hierarchy here, because you have so many agents that they can communicate with each other. So for example, if you have 5 agents and just 2 of them are leader, those 3 still are communicating with each other. They don't need to communicate with the leader, because the leader just need to communicate with one of them. So that's called the fully distributed control.
Okay, thank you, Professor.
You can read those papers. I think that both papers are already published. So you can look at that one. If you have questions, just let me know. We can discuss more detail.
Yeah, I will follow up with you. Thank you.
No problem.
Okay, so we do have some question in chat, but I see a hand raised. Robin, would you like to make a comment?
Yeah, thank you, Saeed. It's very, very stimulating. I'll have a seminar next week about how to dramatically reduce the size of the models for the entire interconnection. So,
oh, that's great. Great. Yeah.
So I think my question for you is, with all the retirements of the coal plants and some of those plants that contribute a huge amount of fault current being replaced by solar systems, which provide zero fault current at zero voltage, what do you think the impact's going to be? Is anyone looking at, what's going to happen in 10 years with the massive retirement of the coal plants and the very large amounts of inverter-based devices throughout, say, the Western interconnection?
Yeah, that is perfect comment. So yeah, that is the issue for fault current contribution and also the grid strength. So people, there are so many approaches people are following. Some of them, they say that oversize the inverters such that you have more current contribution, or using the synchronous condensers, so just for contributing to the fault. So these are 2 main solutions that people are following that one, because as you said, that when the fault happens, you have to have certain amount of the current. So if you just go by optimal sizing of inverter, it's not possible. Or yeah, exactly. So these are 2 things that I'm aware of. Yeah.
Great. So, Saeed, a follow-up question I'll read from the chat. So how do we adapt the current fault location techniques for the converter dominant power systems, specifically to handle the issues with low inertia and bidirectional power flow? I think that question naturally flows from Robin's comment. So if you can maybe put some of your thoughts here for our attendees.
So that fault location for when you have basically low fault current contribution.
Basically, how do we adapt the fault location techniques that we have right now to this changing system? What is needed for us as we are going towards this low inertia and bidirectional power flow kind of setup? How can we adapt what we have right now, or do we have to completely overhaul the system?
No, you don't need to do that. So as far as that couple of issues. One is that the fault level is so low that you cannot even detect the fault. So that's one issue. So that if you go to that level, as the comment with Robin, we have mentioned that you have to have certain way of the increasing the fault current, either oversize the inverters or install the synchronous condenser. There are some other algorithms as well. People talk about that, like because these are not new type of problems in terms of protection. In the protection community, we have so many solutions for this one, like the injecting certain harmonics and so on and so forth. But these two are more feasible solution that I can think of. But if the fault is still, you have large integration of the inverters, but you have acceptable amount of fault current that you can detect the fault. So in that case, what happened? The issue is that bidirectional power flows. And how do you model these inverters in your fault location algorithms and so on and so forth? So that's a complicated task that basically we are going through, because when it comes to inverters, each manufacturer, they have their own models and they are working based on a model. So the issue is that how do you do the fault location identification using the limited information of inverters? At the same time, you don't have enough measurement available, real-time measurement available in the system. So therefore, these are the challenging problem that arises due to large integration of the inverters when still you have acceptable short circuit current. But if you don't have acceptable, and then again, when I'm saying that acceptable short circuit current, it means that to whom it's acceptable. So if you talk about centralized, the substation-based fault location, that's one issue. Another is that how do you develop the distributed fault location? Basically, that protection, that project, that DOE project that we have. So basically, we are working with Georgia Tech and Dr. Sakis Meliopoulos. He has done so long on the distributed protection algorithm. So the promise over is that you distribute the control and protection, everything. So then in that case, you have measurement closer to fault. So therefore, still you can detect that. But if you want to rely only at the substation data, then that would be challenging. So basically, in some cases, you cannot detect the fault. Any other questions or?
Yep. So we do have other questions, but let me try to combine this one.
So I make my responses shorter. So yeah, that because I can go on and on and on. So yeah, just let me know so I know that I shorten my responses. Yeah, go ahead.
Sure. So this is, I guess, kind of final question, and we'll very much appreciate your comment on this. So the question is on, you worked on the co-simulation, right? And you talked about the inverter-based resources. I think this question is interesting from the perspective that how do you model the power systems and power electronic converters together while, with our different level of nonlinearity, different time scale of operation, different, modes of operation? How do you model them together? And I think one thing that is specified is probably co-simulation is a way to do that. So, or maybe you have other comments on this as well. That's part one. And the part two is that if you think about co-simulation as possible approach to really model these systems, what are the available resources or tools that we have that can model these, inverter-based resources in the details that we want to study using this co-simulation framework?
Yeah, that's a good comment. So it depends on the type of a study you do. Sometimes you need to go through the detailed response. So therefore, in that case, you should co-simulate. You have some sort of co-simulation of the PSCAD type of software and PSSE type of software. But sometimes you go through the aggregated dynamic model of the system. So therefore, this nonlinearity totally depends on what kind of a study you are doing and where there are contingents, because the simulation time is also important, because when you work on the grid integration impact assessment, so you may have several days of simulation, so you cannot go that much detail. So therefore, you should kind of see that where the scenarios that you are studying, if it is more close to wind farms, so therefore you have to have detailed model. If it is further away from that one, you can have an aggregated dynamic model. But how to aggregate that? That's one of the projects that we are doing. So basically in that piece, so how to still limit the computational burden, but still you get the acceptable result. So therefore, the response to this comment is that it depends on your study and the scenarios that you are studying. And based on that, you should pick up which one you go. Because there is a famous saying that's killing the mosquito with cannon. So you don't want to go through that one. So you want to go by depends on what kind of a study you have. And the main issue is that computational time. But the most accurate one is that you go by co-simulation of the PSSE and CAPE, PSCAT type of thing. So for the inverter, go to the time domain. For the stability study, go to the sequence domain. Yeah.
Great. Excellent. Thank you, Said, for the presentation today. It was really interesting to learn about different projects in this domain that you are doing, and thank you for answering all our questions.
Thank you.
Yeah, we'll consider it done for the seminar for today. Thank you everyone for attending the seminar, and we'll see you all next week. Thank you.
Yeah, thank you for having me. And
it was a pleasure to have you,
yeah,
of course.
Yeah,
yeah.
it's a
Thank you.
pleasure for
Bye.
me. Yeah, have a good day. Okay,
yeah,
bye.
Good day.